Okay, so this is the angular momentum of an object that's moving. So I started with the definition of angular momentum. I put in torque, I made a substitution, and now it's down to what looks like linear values. So let's look at this. MRV sine theta. Let's go back up here and look at this picture right here. So if the angular momentum of this object right here is MRV sine theta, what's happening to R and theta with respect to this point P on the ground right here as my object moves to the right? R is decreasing, and what's theta doing? Increasing. So what could you say about the angular momentum of the object here compared to the angular momentum of the object there? If it's not speeding up, it's not slowing down, this thing's just moving at a constant speed, it would be the same. What if this distance right here, so I'm going to call it capital R, this distance right here, from the point on the ground to the point directly above P where this object, so this is an airplane flying over you, something like that, okay? So the angular momentum of that object should be mRV sine theta. What is the angle between this velocity and R? Let me make that a capital R. 90. What's the sine of 90? 1. So the angular momentum of a point mass moving at a distance R from a interesting spot usually is MRV, Mr. V. All right, so let's put all this together. So the angular momentum of an object, MRV, but also because of my cross product substitution, that means that my angular momentum is actually, remember, momentum is a vector, but it would be R cross V, which is the same thing as MRV sine theta. This is the cross product. I don't expect you to have to solve cross product questions, but at this point it's nice to respect the cross product exists. All right, how are we going to apply this conservation of angular momentum business? Well, there's all kinds of really cool collisions we can do now. For example, we can have, if you're looking down at a table, we can have, oh, I don't know, maybe this is like a flat ruler on the table, and we slide some object towards it. They collide, and then after the collision, after the collision, maybe this object kind of goes off that way. And what's your ruler going to start doing? Oh my gosh, it's going to spin. Yay! It's great stuff. So now we have to look at objects and consider the conservation of linear momentum during a collision and the conservation of angular momentum during the collision. Okay? So let's look at an example. What if we have a rod on our flat table, but this rod is not free to move. We have pinned the rod down right here. And this is all frictionless. So the length of this guy right here is L. The mass of this guy right here is, we'll call it big M. And maybe we have a little puck over here with a mass of little m. And our little puck of mass little m is moving to the right with a speed v, and it is going to strike the end of this rod and stick. It's been treated with a super sticky physics solution so that they stick on contact and it'll rotate. So this is an overhead view. So then after the collision, I expect this system, pivot point there, sticky object here, he's little m, this is big M, and I expect them to be rotating. Okay. During this collision, is there anything that's applying an outside force to this system? The pivot point. So it applies an external force. Is it applying an external torque if this is the pivot point and torque is F times R? No. So is linear momentum conserved in this collision if there is an external force? Okay, so momentum is not conserved. Oh my gosh, is that the first time you've ever seen me write that down? But what is conserved? Angular momentum is conserved. So this is why we have to understand how to apply angular momentum to an object that's moving in a straight line. Because even though this guy right here is not moving in a circle, the moment that it collides with and sticks to the end of our big mass here, that collision is then going to result in rotation and the angular momentum will be conserved. So what's moving before the collision? Little m, big M, or both? Little m. So if angular momentum is conserved, we'll have the angular momentum initial is equal to the final angular momentum. In the beginning, it's a point mass. And how do we solve for the angular momentum of a point mass? M, R, V. What's R going to be for my picture that you can't see anymore? L, the length of the rod. And what's V? V. Yay. Now afterwards, they're actually rotating. And so our angular momentum here should be I omega. And they stick together. So what can you tell me about omega of the system when they stick together? It's the same. But what is the moment of inertia of this system? I is moment of inertia. This is a rod pivoted about its end with a point mass stuck on the end of it. Does anybody remember how to find the moment of inertia of a rod? About the end? Okay. And then what about the point mass? Do I need to calculate, or do I need to add its moment of inertia too? Yep. So 1/3 big M L squared takes care of the moment of inertia of the rod, plus then what was the moment of inertia of the little guy? MR squared. So what's R going to be in the case of my picture? L all squared times omega. So, can we find this angular speed of the system after the collision in terms of m's and l's and v's? And there you go. We could simplify, and you'll see, because I think some of you don't like the 1/3 on the bottom like that. Would it be 3mv over ml plus 3ml? Would that be a nice simplified answer? Do you have to simplify it? Not for the purposes of AP Physics C, you don't have to simplify it down. Any questions about that?